Right. So today is it's week 5, variational autoencoder. So it's VAE. Topic is we're going to talk about generative autoencoder. So we've talked about autoencoder a lot last week, and we're going to talk about what if we want to generate samples using autoencoder, because autoencoder is just it's a compression and decompression. It's an encoder decoder architecture, and people use it for mostly compression, but there are exceptions. We talked about sparse encoding, but that's kind of a special case. So when we have a compressor, how do we make it, turn it into a generative model? And then when we talk about VAE, there's a prerequisite, which is variational inference or variational Bayesian inference. So we need to talk about the math a little bit before we dive into VAE. So we're going to talk about VI, variational inference, for a bit, and then move on to variational autoencoder. Then we're going to talk about how to actually train a VAE, because there's something called reparametrization trick that is involved. Okay, so generative autoencoder. So I hope that everybody still vividly remembers what autoencoder is. So it consists of an encoder and decoder. You put the image in, and then it compresses. Then you get the latent representation, or the code, or the latent variable z here. So this is your x, this is your input, which is 784 dimensional input, and then you turn it into 4-dimensional. In this example, it's a 4-dimensional z, and then you decompress it into the original 784. Is it 4? It's 24. Yes, it's 784. Yeah, and you call that x prime, and the objective is to make the x and x prime as close as possible. So we use the MSE, the mean squared error loss, to train on the autoencoder. Yeah, by the way, if you have any question, just yeah, you can speak up or you can type it in the chat box. Any question regarding autoencoder? I think it was a pretty straightforward model class. It's not very complicated. You just use several nonlinear layers for encoder, the same for the decoder, and then you just use the MSE loss, and that's it. Right, and the bit of a mathematical notation. So we had the z converted from the x that goes through a nonlinear function f, and the x prime is, again, you put the z through a nonlinear function f, and well, actually this should be a different f. Sorry about that. So this should be, maybe this should be g, because it's not, you don't have to use the same nonlinear activation function for the encoder and decoder. It could be a different combination. We talked about it in pretty lengthy detail last time. Anyway, so yeah, I'm just gonna erase that. Right, yeah, so you put it through another nonlinear layer, and then you get the x prime, and then you do this least squared error, which is this mean squared error. So yeah, as I said, this is we call this z information bottleneck. You compress it into a lower dimensional space, so the autoencoder is forced to learn important features that helps it reconstruct x prime. So it needs to choose the kind of information that it wants to retain and just throw away the noise. So that's where the information bottleneck comes in. And as you can remember, hopefully this inputs the x samples that are similar in the original space, in this case, in the original 784 dimensional space. The similar inputs would lead to the similar z's. So we said that we hope that this pair is similar or closer to one another than compared to like this pair. So this should be like closer, and this should be like farther, right? So yeah, it's just a recap, so nothing too heavy. And we used the lower dimensional space. I mean, we used the latent variable z, and we scatter plotted it on a 2D space. And the way we did it is we used another algorithm, which is like PSNE or PCA or UMAP. We use one of those algorithms specialized for visualization. So we compress the z again into the 2-dimensional space and then scatter plot that. we were able to see something like this. So that was the recap. Now, what do we do if we want to generate new samples? So we've compressed, we have a compressed space. So we can safely compress the original image X into a 4-dimensional space, or in this case, 2-dimensional space, some lower latent, some lower dimensional space. And once you have that kind of model, can we use that model to generate a completely new sample out of it? Because now the space, the lower dimensional space, the Z space, kind of has a meaningful, it has a meaning. It's a rather meaningful space because, as I said, similar pairs or similar X's live in the vicinity compared to completely different samples. So for example, here the 1s live in this region compared to like 3s here, or 2s here, right? So the Z space is rather shaped nicely so that there's like a cluster of things. So given that space, can we generate new samples? Because sometimes we want to do that. I think we can come up with 2 rather simple ideas. One is to perturb an existing Z. So this, there are a lot of Z samples here. So there are a lot of Z samples. I mean, the samples 1 embedded into the lower dimensional space. So there's a lot like here. There are different Z's. So given a specific Z example, Z sample, you could add a Gaussian noise or something. So suppose this is a 2-dimensional Z, which is 0.5 and minus a negative 1.2. Then hopefully, I mean, intuitively, 0.6 and minus a negative 1.3 would probably be similar to the original Z. So this is your original Z, and then this is your Z prime, which is a slightly perturbed Z. And it's reasonable to believe that this is, a new sample. So you could do that, and or you could try to sample a random point from this area. So because this is a area of 1s, this is a subspace in the lower dimensional space. There's a subspace where only the 1s reside. So maybe you can try to sample random points from this specific area to generate images of 1. So maybe just try to get here, you sample from this area, and it's reasonable to believe that they'll all be 1s. So the problem is, I mean, this one is rather simple. Perturbing the existing Z is rather simple. You could totally do that. Sampling from this space is not so straightforward because we don't know the distribution of this space. So we don't know, I mean, unless you do density estimation first and then try to get the distribution of this subspace. You don't know the distribution of this space, so you can't really sample from this space unless you know the distribution. You can assume that this follows a Gaussian distribution or some other distribution, but that's just an assumption because you never know how your autoencoder has shaped the latent space. There's no guarantee that this subspace of 1s follow a Gaussian distribution, so you can't really sample. I mean, you don't even know the mean and the standard deviation anyway. I guess you could try to do a linear interpolation between 2 Z's. There's a Z here, and there's, okay, let me just blow it up a bit. There's a Z here, there's a Z here. So maybe you can try to interpolate between the 2. So you draw a line, and then all the lines, all the dots between the 2. So here, dots here, here. Different ratio interpolation. Maybe you can assume that they're all 1s again, but still it's not really a guaranteed operation. I mean, it would still it would work in a reasonable manner, but there's really no guarantee. So yeah, both. I mean, this is just 2 ideas that I had. I mean, I guess you could come up with a new trick to use the trained autoencoder to generate new samples. But these two are probably the most straightforward way to do it. And again, both are not guaranteed to work very well because we trained an autoencoder. We didn't train a generative model. We trained an autoencoder, so there's no guarantee that it would play the role of a generator. If you have any other ideas how to use the trained autoencoder to generate new samples, you can share that with everybody. This too is all I got. Well, I mean, I didn't spend too much time thinking about it, but yeah, all right, I'm gonna move on. So I actually did one of the operations on my own. So I'm using a autoencoder trained on MNIST for 50 epochs. 50 epochs is like probably enough. Well, I mean, it didn't still converge. It wasn't overfitting. I used the same code from the last Thursday, and set the number of epochs to 50, and still the validation error or the validation performance was still like increasing until epoch 50. But still, it's like enough number of times to see that your autoencoder is doing a good job, because you give the trained autoencoder 9, and then the reconstruction is pretty. It's pretty clean image, so we are pretty sure that it's working okay. And then what I did is I perturbed this Z. So when you put the 9 into the autoencoder, you get the Z here, and then you do a reconstruction. So this is X, this is your X prime. So given this Z, which was 30-dimensional lower, it's from a 30-dimensional lower dimensional space. If you remember the details from the last Thursday, our Z space was 30-dimensional. So I just perturbed Z using noise coming from a Gaussian distribution of this. So this is like Z prime, another Z prime, another Z prime, so like Z1 prime, Z. Yeah, it's weird. Yeah, they're all from the same Z. It's just that you add different amount of noise into the Z, and you can see that they're slightly different, but you can probably tell that they're all 9s. I mean, it's pretty straightforward. So like this one here, this one here, this one here, they all look very slightly different from the true reconstruction, which is here. So perturbing your Z kind of works, and if you add larger noise into the Z, so now you can see that the standard deviation is 1.0 instead of 0.5. So if you add larger noise to the Z, then it becomes a bit more. It's a bit more different. So like this, these three are distinct from one another, and it is also a bit different from the original. I mean, this original image as well. So you could say that it is working, but I would say it's a rather strong claim that they're new images, because they all probably look very similar to one another. I mean, yeah, there's like a missing piece like here. There's a missing piece here, and maybe it's a bit like this here. The stick of 9 is a bit skewed compared to here, but they're still like, it's a very similar shape to the original 9. I mean, the shape, the skewedness, the rotation, the angle, the size of the circle of the 9, it's all very similar. So we're not actually generating different kinds of 9s. So this is all true images of different 9s. And our perturbed examples here and here, none of them are like truly different images. None of them are like really novel. So I would say that perturbing your Z is a rather limited, gives you a limited choice of limited outcome, basically. Right. So yeah. I just gave you thought about this example to share with you guys that perturbing, I mean, using some simple trick on your autoencoder is probably not the best way to make it into a generative model. Any questions so far? Nope. Okay, I'm gonna move on then. Right, so yeah, it was a rather motivating example. So how do we motivating example to derive a actual generative autoencoder, which is basically we're going to talk about variational autoencoder. So before that, as I said, in order to talk about variational autoencoder, VAE, we need to talk about variational inference first. It's a bit of an intro. So it's going to be a bit mathematical, but it's not that it's not impossible to understand it in one go, because I'm going to talk about it in a very high level. I'm not going to talk about actual derivation, like how to actually use variational inference in real problems. It's just going to be like introduction on a high level. Okay, there's a question. Perturbing Z가 너블런스 그러면 GA는 주로 GA는 어디 주로 하려고? GA가 뭔가요? So yeah. Okay, so I just called it a generative autoencoder, but there's no such thing as a generative autoencoder. I just named it generative autoencoder to motivate the students. So yeah, I wouldn't say that. So your autoencoder, just by simply perturbing your Z, doesn't make it into a proper generative model, because it hasn't actually learned the distribution of the X, the samples. It only learns to compress well all the data points in X, and that's it. So the assumption was that the Z space was probably like shaped nicely to facilitate a good compression, but that's it. As far as like generative model goes, it's not a proper generative model because it hasn't learned the distribution of X. It only learned to do the compression and decompression. So I just called it a generative autoencoder, but it's not a generative model. So, yeah, if you want to sample if you want to have a autoencoder that can generate novel samples, you should use VAEs. You don't just train your autoencoder and then just perturb your Z. That's not the way to go. All right. Okay, so the essence of variational inference, or VI, is the posterior distribution. So we're going to talk a bit about the probability. Yeah, it's probabilistic models basically. So given data X and unobserved or latent, or sometimes hidden, I mean, they're the same thing. Latent variable, hidden variable, unobserved variable, they're all the same thing. So given data X, which is observable, and unobservable Z, and we're going to assume that the Z determines X. So X is coming from the Z. So X is what we see in the real world, but its contents or semantics is determined by the hidden variable Z, which is not really accessible to us. And we're interested in the value of P of Z given X. So we want to do it like in the reverse way. So because Z determines X, when we have the X, we want to infer what Z actually is. So it's all like rather abstract, but I'm going to give a concrete example in the next slide. So the usually how X is derived is that you draw latent variable Z from a certain distribution. So Z is also following a distribution, and you draw a ZI, ith example from the PZ, and then given ZI, you can generate, given ZI, you can plug that into the PX given Z, which is another distribution that X follows, and then you plug the ZI into the PX given Z, and then you can draw a data point XI. So that's how people assume that the X is generated, and you want to infer PZ given X. So when you have X, you want to retrace back to the origin Z, like if you see an X. So that's the posterior distribution. Like sometimes you really want to learn this in a lot of concrete real world application of machine learning. So yeah, there are two examples. So topic. So Z is like, if you are familiar with natural language processing, Z is usually called the topic. And when you are dealing with document clustering or document classification, Z is usually called the topic of news. If you're given like some article, newspaper articles, or some documents, like there's a Z, which is a distribution of topics. So Z would be like Z could be a three-dimensional space where first dimension is it's a topic for like this represents sports, this represents politics, this represents I don't know, science, and your x is coming from a distribution of z, so it's a multinomial distribution, so maybe it's like 0.3, 0.1, and 0.6. Then given this z distribution, your x is determined to have this kind of semantic, or this ratio of contents. So if you assume this, then given a document, given a newspaper article or given document, you want to reinfer the true z given the document. So that's where pz given of x, the posterior distribution, comes in. Or in our case, we have an autoencoder. So z is a latent representation of a MNIST image. So we can, I mean, in the autoencoder, we derive z given x, and then we decompress it into x prime. But maybe if you can think about another way to describe an autoencoder is you have a true z that lives in the latent space, and x is derived from it. So there's a latent representation z, and your MNIST images are coming from this. So your images are determined by z. So given then what you want to do is you want to have a posterior distribution where you derive the latent representation given the MNIST image, which is essentially an encoder, right? Because encoder derives the latent representation given x. Yeah. So yeah, posterior distribution. It's you want to estimate it, or you want to learn the posterior distribution for these kind of purposes. So yep, the problem is usually a true posterior distribution is I'm sorry, this is a typo, is intractable. So following the Bayesian principle. So I hope you guys are all familiar with Bayesian principle, which is basically this. So if pz given of x is px given z times pz divided by px, right? So this is pretty straightforward. If you multiply both sides with px, then pz given x px equals px given z pz, and they're both just joint distribution of z and x, right? So pretty straightforward. So it's a Bayesian principle. So this you can. So if you want to learn this, then you need to learn these three components, like here, here, and here. This you can probably estimate. It's a likelihood. Like given a z, how do you derive an x? So you can actually assume that it follows a certain distribution, and you can learn that. And pz, you can also assume that it follows a certain distribution, like some multinomial distribution in case of a topic distribution in newspaper articles. Maybe it could follow a Gaussian distribution if you think about some other application. The problem lies in the denominator px, because it's a p of x, which is just a distribution of your sample, which is just gigantic space. Like you're like, how do you define, if we're talking about MNIST images, how do you define the distribution of MNIST images? Like nobody really knows, and you can try to infer it like this. Or more concretely, yep. So right. So it's the same. This, like, I just convert the denominator into like a likelihood, like a conditional distribution, and a prior. So, in Bayesian principle, this is called prior. This is called the likelihood, and this is called the evidence. So I just converted the evidence to look like the numerator, and well, as I said, you can probably you can assume that this follows a certain distribution, this follows a certain distribution. So maybe you would wonder if you also already know the forms of these, so you can probably calculate the denominator. And the problem is that for a very small z, Like I don't know, if you're talking about the multinomial distribution, then you can probably do that. Like if Z is like a three-dimensional space, then this becomes like it becomes a not an integral, but a sigma, because we're talking about discrete variables. So if Z is a discrete variable, so if Z is a discrete variable and it's like this, the dimensionality is really low, like you can take only like 3 values or 4 values, then you can safely calculate this, like this just a loop, like a for loop for like 4 values or like 3 values. But if the Z can take a lot of values, like if the Z is like a high dimensional variable, even if it's a discrete variable, then this quickly becomes pretty like a burdensome job. And if Z is a continuous variable, for that matter, if Z becomes a continuous variable, then there's infinite amount of values that Z can take. So there's no actual way to actually, rigorously do this and then get the denominator. And usually there's no analytical solution for actually solving this integral. So you have to, you either go through one by one doing a for loop, or you have to actually integrate it using some numerical solutions, or maybe you do Monte Carlo sampling. But usually it's not a fun thing to do. So denominator is this is a reason for the intractableness of the true posterior distribution, right? So this is our problem. So we want this, but this kind of blocks us from actually getting this. So yep, yeah, this is often combinatorially large or even infinite. Like Z, if the Z is continuous value, then it is infinite. So, yeah, this is the pain point. So instead, what we do is we instead approximate it with a simpler function, Q. So this is so we have to like make compromises, because we can't actually compute the true PZ given X. So we actually just assume that it follows a simpler distribution, often Gaussian distribution, and then we be done with it. Like we're content with it. The question is 분자는 다룰 만한가요? So which means that are the numerators easy to treat compared to the denominator? And the answer is yes. Yeah, as I said, you can assume that Px given Z follows a certain distribution, and Pz also follows a certain distribution. Usually both can, like maybe Pz follows some multinomial distribution, and Px given Z also follows multinomial distribution. Then then you can safely get the Pz given X. And if there's like Pz, as I said that the Pz is a prior. So if your likelihood and if your prior and if your likelihood, no, I'm sorry. So yeah, if your posterior distribution Pz given X follows the same distribution as Pz, which is like if both are like multinomial, or if both are like Gaussian, then you call the, I'm sorry, yeah, I'm kind of getting confused with the conjugate priors. I guess yeah, I guess we don't have to go into the detail, but what I'm trying to say is, like, this is very treatable, because you assume that they follow a certain distribution that is like analytically, solvable, or it's like you can totally do it with a simple program, or you can even do it with your pen and paper. And a nice choice of Px given Z and Pz is such that the distribution of Px given Z and distribution of Pz given X is the same. Like after you derive your posterior distribution, it's the same distribution as the starting likelihood distribution. Like both can be multinomial, or both can be Gaussian, or both can be Bernoulli, like binomial, something like that. So in order to do that, you need to have a specific choice of PZ. So if you want this and this to be multinomial, then this needs to be like a Dirichlet distribution, something like that, and that you call it a conjugate prior. So yeah, it's totally treatable. The problem lies in the denominator. Q0 근사한 수학적인 근거는 있는가요? 수학적인 근거. So there's no mathematical. I mean, it's kind of a like forced choice. because you can't actually derive the true PZ given X, true posterior, there's no way then, like, approximating with a known distribution Q, which is usually Gaussian, is kind of a compromise, the only thing that you can do. So I guess that makes it a mathematical evidence. Yeah, it's a practical compromise. And of course, if you use a very complex Q, if you use a very, very complex Q, like, then you might be able to, the approximation, the quality of the approximation would be really, high, because, like, if, for example, if your true PZ given X, the true posterior, if it looks like this in a one-dimensional space, like this is your Z, and then this is your likelihood, and your, well, like, for example, let's say your posterior has 3 modes, like mode 1, mode 2, and mode 3, and you're using QZ, which is a Gaussian distribution, then it will, there's only one mode, so it either looks like this and you are satisfied with this looking Q, or another choice is maybe you try to contain everything. And in this case, yeah, it's not a very good approximation. It's kind of a bad compromise, but that's, you're left with this because you assume that the Q is a Gaussian distribution. But if you use something a bit more complex, if you use like like a mixture of Gaussian, then yeah, if you use 3 mixtures, then you can actually approximate the 3 modes like this. So the more complex function you use for the Q, then the higher the quality of the approximation would be. But then it'll be, again, it's a trade-off. If you use a complex function for Q, then it'll be harder to approximate P. So there's always trade-off. Why can't we assume any simpler distribution for PX? I guess you could do that. In that case, I guess things would be really, really simple. But yeah, if you assume that PX follows a simple distribution, then again, your PZ given X would not be really realistic. So if you assume everything like very simple for all these components, then PZ given X would be also simple, and then it wouldn't actually, resemble the true nature of your data. So even if you have posterior, it wouldn't really describe it wouldn't really be true posterior, because you're assuming some very simple distribution for PX. Yeah. Yeah, it's like the choice of Z, the latent variable, is pretty much up to you, because you are the one making an assumption that X comes from Z, and you can make certain assumptions about how the Z looks like and how X is sampled from the Z. Like, you can do that, but PX is a fixed reality. The data set is given to you, so there's not much you can do or you want to do with X, because you don't want to assume too much about the distribution of X. You can do a lot of things with PX given Z and PZ, because that's up to you. But PX is not up to you. It's a fixed reality. So yeah. All right. So as I said, yeah. So this was a motivating part why we want to approximate the posterior with a simpler distribution, usually Gaussian distribution. So our objective is we want Q to be as similar to P as possible. So because that's what approximation is, and we usually use a Kullback-Leibler divergence, something called KL divergence. It's so the mathematical equation looks like this. So KL divergence between Q and P. So it's 2 different distributions. Q is a distribution, P is a distribution, and we are calculating how different they are. So it's divergence between Q and P. So DKL. So of course, if they're the same, then the divergence would be 0. So mathematical notation looks like this. So you have a QZ and log QZ over PZ given X. So Basically, like it's a Q here and then P here. So because there's Q here, there's P here. So that's the mathematical notation. Like DKL XY is it's X log X over Y. So yeah. Right. And of course, yeah, I'm using sigma because I'm going to assume that z is a discrete variable. But if z is a continuous variable, then this needs to be an integral, obviously. Right. So if you assume that the q and the p are the q and p are the same thing, if they're the same, then this becomes 1, right? Because they're the same thing. So log 1 is 0. So then your divergence becomes 0. So the only way that your DKL divergence could be 0 is when your Q and P are the same distribution. If they're slightly different, then it'll be some positive value. And the thing to note is that DKL divergence is not symmetric. So DKL Q P is not the same thing as DKL P and Q, right? I mean, you can tell from the equation, like it can't be the same. So it's not a distance. So distance is like usually distance like satisfies Jensen's equation and all that, and it must be symmetric. It must be like positive and all that. Divergence is not distance. Divergence it doesn't need to be a symmetric thing. So yeah, and this formula usually what people do when they use KL divergence is they put this true distribution, which in our case is the P. They put the true distribution here and the approximating distribution to the right. So that's your usual KL divergence. And what we're doing here is a reverse KL. So we put Q in the left and the P on the right. So it's a reverse KL because the one that is approximating is on the left and the one that is true is on the right. So it's a reverse KL. There's a difference between the two. Like if you're I guess I can draw a picture. If your P looks like this, if your true P looks like this, then if you use reverse KL with the Q being the Gaussian distribution, then the Q would look like this. Maybe I should use a different color. Yeah. So in a reverse KL, your Q would try to look like this, and in the I guess like the original KL, your Q would look like this. So there's a difference between the two. So what I mean, you can imagine why one like sometimes you want to use one choice over the other. Like, what would happen if you used the original KL? This is the original KL, and the green one is the reverse KL. You could imagine the behavior of your Q in both cases. And for example, if you use the reverse KL, then you won't be able to draw samples, or you won't be able to describe this region here. There's obviously a mode. There's a positive, positive amount of information in this region, which is a true P, and because you're using a reverse KL, you're completely ignoring this mode, and then you won't be able to draw examples you won't be able to draw Z that describes this region, right? So that's the limitation of reverse KL. But the upside is whatever you draw from your Q, from your reverse KL Q, it will always be a legitimate sample, right? Because it is following the true distribution, at least in this region, it is following the true posterior distribution. So whatever Z you sample from your Q, it'll always be true. It'll always be a legitimate Z. But in the other case, in original KL, you are likely to draw sample, or you're likely to draw Z's from this region, which is in fact not a, you know, there's not much information, there's not much Z's living inside this region, because it has lower probability in the true posterior distribution. True P, there's not much Z, there's not much going on in this range. But since you're using the original KL, there's like a hefty amount of distribution assigned to this region. And when you sample from your original KLQ, you're likely to sample from this region, and which doesn't actually describe the true posterior. So there's upside and there's downside. Upside of original KL is that you try to cover the entire entire posterior distribution. So, you know, you won't be missing anything. Like you're covering this, so you're not missing anything. But the downside is, when you sample stuff, there's a chance that it is coming from a lower probability region. So yeah, reverse K and original KL have a upside and the downside. There's a pros and cons. Yeah, you could say that the narcotic. Yeah, you could say that you want to at least approximate one mode as accurately as possible. Yeah. So yeah, when you have learned the posterior Q, approximate posterior Q, at least you want that Q to be the Z's to be coming from the legitimate subspace of P. And I think there's also mathematical reason behind it. Like if you use original KL, then your variational inference would look like a very different thing. I guess if you use the original KL, it's not even called a variational inference. There's probably some other name. I forgot what the name was. But when you're doing variational inference, it has to be the reverse KL. So it's a DKL, Q, and P. All right, I'm gonna move on. All right, so there's some expansion. So you have the KL divergence, and then you can, because this is P Z X divided by PX, right? So you put the PX outside this term, which becomes a log PX, and log PX, and this is kind of like an expectation over the Q distribution. So you can, because this is an expectation, you can separate the first term and the second term. So this becomes the first term, this becomes the second term, right? Because sigma Z over QZ is an expectation, and you can separate the numerator and the denominator, because it's a log function. So this is the numerator, this is the denominator, this is the second term. So far so good, I hope. And the reason that we can come from here to here is that your log PX has nothing to do with QZ. Your PX is a fixed term, right? It's your data set. So it doesn't really, whatever you do with your QZ, whatever approximate posterior you learn through Q, doesn't really affect your log PX. So log PX, you can just throw this away, and then this becomes log PX. And then, as I said, sigma Z over QZ is an expectation over Z. So it's just, you just transform this into an expectation, and that's it. So you're left with this. So it's a simple manipulation. You have the DKL, and then you manipulate it to get the final equation right on the bottom. Another question, forward K를 사용하면 unknown P 샘플링을 해야 하는 건가요? unknown P 샘플링 하는 게 아니라 P는 어차피 unknown이고요. 이제 true posterior는 어차피 알 수가 없고, 이제 그거를 approximation 하기 위해서 이제 Q를 사용하는 건데, 우리가 이제 reverse K를 사용하면은 Q가 적어도 true posterior가 뭐 이제 상상인데 이렇게 생겼다. 근데 우리가 reverse K를 사용하면은 적어도 Z가 존재하는 곳으로부터 이제 Z를 뽑을 수 있는데, 그러니까 이제 왜냐면은 리버스 K를 사용하면은 Q가 이렇게 생겨 먹었을 거기 때문에 이렇게 생겼으면 당연히 이제 Q를 배운 다음에 Q에서 Z를 뽑으면은 여기서만 나올 테니까 이제 제대로 된 P에서 나온 거랑 비슷한 효과가 있는데, 이제 이걸 forward K를 사용하면은, 뭐 forward K를 제대로 맞는 말인지 모르겠죠. forward K를 사용하면은 Q가 이렇게 생겨 먹었을 거기 때문에 거기서 이제 Z를 뽑으면은 요 구간에서도 뽑힐 확률이 높은데, 요 구간은 사실 뭐 P의 확률이 되게 낮은 구간일 수도 있다는 거죠. 왜냐하면은 forward K를 사용하면은 P가 넌 제로인 곳을 전부 다 커버하려고 이렇게 학습이 되기 때문에 이제 하나도 빼놓지 않고 모든 그 그러니까 이제 서포트라 그러는데 모든 논제로 probability 스페이스를 전부 다 Q가 커버하려고 그러기 때문에 이제 그렇게 되면은 이렇게 확률이 낮은 곳에서도 이제 Z를 뽑게 된다. 그래서 이제 그것을 우리가 원하는지 안 원하는지에 따라서 forward K를 사용할지 리버스 K를 사용할지 정하게 됩니다. 네. All right, so as I was saying, you do a simple manipulation and then you arrive here. So your DKL is like this now. And then you can shuffle the terms a bit. So you leave this here and then you just simply put this onto the left. So this becomes DKL minus EZ log QZ negative, like minus log P, whatever. So so the point here is that the left side, the log px, is a fixed term because your probability distribution over your data set is fixed. It doesn't change. Whatever you do with variational inference and Q and all that, your px to true distribution doesn't change because it's as I said, it's a fixed reality. So the change that whatever you do with Q, the only change occurs in this region, in this right-hand side, and you can say that it is fixed. Like since log px is fixed, your right-hand side will be fixed. So you can assume that whatever you do with your Q, there's a trade-off between this term and this term, right? Because if you increase this by somehow manipulating your Q, and then this term must also this term must decrease. I mean, if you think about like per plus, there's a plus here and then it's a negative easy, then if this term increase, then this term must decrease, and vice versa. If you do something with your Q and somehow you decrease like this term, increase this term, then this term will decrease. Basically, like there's like a trade-off. So that's because, as I said, the left-hand side is fixed. So if whatever you do with the Q, there's a trade-off between the two terms, and you can assume that what the objective of variational inference was to minimize the distance, or not the distance, the divergence between Q and Q. It was to minimize the Kullback-Leibler divergence, scale divergence between the Q and P. So what you want to do is you want to maximize this term in order to minimize this term, right? Because as I said, there's a trade-off. So if you maximize this term will automatically be minimized, and you want to do it in such a way that this is like, minimized to almost to the extent that it is a zero, which, I mean, theoretically, this becomes zero. So you call this part, including the minus sign, the negative sign, you call this part evidence lower bound, or elbow. If you read like variational inference papers or VAE papers or some papers, you often run into this term elbow. So this is what that elbow is. So you want to maximize the lower bound. So like lower bound being like, your log px has a certain probability, certain distribution, and you want to, and this term becomes the lower bound. And if you maximize this, like this is your px, this is your log px, and this is your. I'm sorry, it's probably not. There's like certain probability in the y-axis, and this is your log px. This is your evidence lower bound, elbow. Then the difference between the two is this one. So this is your difference, DKL QP. It is the difference between the true log px and your elbow. So you want to maximize, so this becomes your lower bound because DKL is always positive. It's either 0 or positive. It can never be a negative value. It's a divergence between two distributions. So DKL is always non-negative. So that's why elbow becomes a lower bound of the log px, and you want to increase your lower bound. So as you increase elbow like this and this and this, that means reversely your DKL is being minimized and minimized, and it's become smaller and smaller and smaller, and that's what you want. So that's why the word, like the term lower bound is there. All right, yeah, so maximizing the elbow leads to minimizing DKL because log px is fixed. So this is fixed, so you want to maximize this term in order to minimize this term. All right, so I hope this elbow thing is all clear to everybody. Yeah, I'm gonna move on then. The good thing is QZ and PZX is rather treatable. So it's unlike the PX term here. You can assume that they take a certain form. So like, I mean, QZ is obviously like usually a Gaussian distribution. This is also some similar to Gaussian. This also can be a Gaussian distribution. Then they can be analytically, treated with pen and paper. So what we did is we converted an inference problem because we wanted to infer PZ given X. So we wanted to sample Z, or we wanted to learn the distribution of PZ given X. And we turned that inference problem into an optimization problem. Why is it an optimization problem? Because we have a term that we want to maximize. So it's an optimization problem. If you remember optimization, there's a certain objective function and you want to minimize it or you want to maximize it. And if you want to minimize it, you use gradient descent, right? So what you can do is you can take the evidence lower bound and try to maximize it, or reversely, you can minimize the minus elbow term. So it's an optimization problem now. So it's a pretty neat problem. So yeah, and if you're using the Gaussian distribution for your Q, then what we're doing is, what it boils down to, learning its mu and sigma, which is the mean and the standard deviation, right? Because Gaussian distribution is semantic, or its distribution is determined by its mean and sigma. So when we are learning or optimizing the elbow, what we're doing is we're learning the mu and sigma of your Q through maximizing this term. And you can do it iteratively using gradient descent. Or in this case, it's maximization, so it's gradient ascent, actually. And yeah, optimization problem is easier to handle than inference problem. Right. Oh yeah, it's just a caveat. So not caveat. It's just additional, just for FYI, for your information. So evidence lower bound LQ is often called a variational free energy because if you rearrange the terms here, including the minus sign, rearrange the terms, you get this. So yeah, it's just if you expand this, then it's just simply EZ of log P Z comma X and minus EZ log Q Z. And this, and this is your entropy, right? Entropy. This is your information entropy. So and the entropy and all that comes from like the physics. So it's called, like, you have like a physical system and there's like an energy, like there's like a closed system, and then there's like particle moving around, and this is all coming from the thermodynamics and stuff. So you can call this also variational free energy, but I'm not sure if people use that term a lot in the machine learning literature. I've seen that like once or twice. I've seen some people describe the elbow term as a sum of the joint distribution with the entropy, and they try to do something with the entropy, or they try to do something with the joint distribution. But yeah, these days not so much. All right, yeah, this ends the kind of a theoretical, like very simple theoretical background of variational inference, and then we're going to use this to derive the variational autoencoder. or rather, understand the variational autoencoder. Why there is a term variational in front of autoencoder. Yep. Yeah, in VAE, the objective is to compress X to Z, and we want that Z to follow a certain distribution. So in that case, we can sample from PZ given X and then generate a new sample, right? So that's the difference between an autoencoder and a VAE. In VAE, we want the latent space Z to follow a certain distribution. And in order to force that, you need to do some regularization. So yeah, objective is compress X to Z, which follows, this is the new part. Before it was just compress X to Z, decompress decompress Z to X, and that was it. Now there's a new term here, which changes everything. Right, and we're gonna assume that this follows a distribution, typically Gaussian distribution. I mean, or yeah, almost always Gaussian distribution. So we assume that the Z, PZ given X follows a Gaussian distribution, and in order to do that, encoding becomes your approximate posterior. So this is your posterior distribution because you're deriving Z given X, and ideally we want to learn the true posterior PZ given X, but again, as I said, this is almost impossible to do it. So you rather use a learnable function Q to derive your Z, which is and your Q becomes an approximate distribution of Q, approximate distribution of P, and you call it Q, and that becomes a encoder actually. And the decoder is now a conversion from Z to X. And both are neural networks because encoder is neural network, decoder is neural network, right? So you're using neural networks to basically learn your posterior distribution, like approximate posterior distribution. And I said that you're forcing the Z space to follow a Gaussian distribution. So you need to have a KL divergence between your Q and your PZ, which is Gaussian distribution. So you're assuming, this is your assumption, you're assuming your Z follows the Gaussian distribution. So PZ is a Gaussian, is a unique Gaussian, like mean being 0 and standard deviation being 1. And you want your posterior distribution to be similar to your P. So that's why the KL term comes in. I said the KL term is for minimizing the divergence or the difference between, I mean, KL divergence measures the difference between two distributions, right? So, yeah, so encoder, decoder, KL term, that's it. Okay, there's a question. LQ, so yeah, PXZ 대한 인티그레이션 어려워. Bayesian Principle 이용하지 못한다 하셨는데 LQ에서. Yeah, that's a question. That's a good question. I was not really. I always had a question, like wondering myself that why PZX, log PZX is easier to handle compared to denominator in the true Bayesian principle, in the Bayesian form. Let me see if I can explain that in using the previous stuff. Oh, sorry. I guess there's one difference between the previous one and this one, which is a log term in front of PZ even PZ joint and log term in front of the joint distribution. So, I mean, you can try to manipulate it into like PX given Z and then PZ, which is basically a joint distribution, and then there's a log term in front of it, and then you can separate the two with a log PX given Z plus P log PZ, which is way more like, easier to handle compared to a joint distribution, because you can assume whatever form that it takes whatever like distribution the px given z takes, and you can also assume that pz also follows a certain distribution, usually Gaussian in both cases. And if you put log in front of Gaussian, then that becomes like way easier to handle, because in the Gaussian distribution there's exponential term. So I guess it's just easier to manipulate stuff when you have this form instead of the true Bayesian principle. But I still it's a rather, I guess that's a pretty vague answer. You can look it up on the Wikipedia page and go through actual example of how you can manipulate p, z, comma, x, the joint distribution, assuming that they're like Gaussian distribution. And yeah, and then like, yeah, there's a concrete example. I guess do we have, yeah, it's already 36. So yeah, if you I could give you a pointer to the concrete example. But normally in VAE we don't deal with the joint distribution anyway, so we don't need to worry about that. But yeah, I can post some pointers on Classroom after this. All right, I'm gonna move on to the right. Yeah, so yeah, compress x to z, which follows pz given x, decompress x. So VAE allows us to map data distribution px to a probability distribution pz, which is approximate, of course, because we're using approximate distribution of q to map x to z. But anyway, so we can do that, and then after that we can sample from pz, which can be converted to x. So now we're guaranteed that, I mean, if you learn a proper VAE or proper q, then whatever sample you use, whatever z that you sample from your like latent space, it can be safely converted back to the x, the given data set. So which is the major difference between the autoencoder and the VAE, right? So in order to do that, then your objective function, there needs to be some changes to your loss function or your objective function. So of course you need a reconstruction term. It's still a autoencoder, right? So you still need the reconstruction loss, and then there's an additional term that you need to use to enforce this, that the fact that z follows pz given x, which is Gaussian distribution. So in order to do that, you need a regularization term. So here is the, this here is the reconstruction term. So this is your, as I said, this is your decoder network, and it's parametrized by Greek letter phi, I think. So this is your decoder network, and you're maximizing the log likelihood of your data x. And usually this can be just converted to change the reconstruction loss. You're trying to maximize seeing your data given z, right? And seeing your data means it is the true data or the reconstructed data. So log p phi x given z can be safely converted to a reconstruction loss. And you can just think of this as you're sampling from the z, which is you're sampling from the posterior distribution, which is the q function. So you encode your x to a z space, and then you can sample from your z space, and then you can convert your z to a x, and you want to maximize the chance of that being a true x, which is a reconstruction loss. And here you need the regularization term. So you want your KL divergence between your posterior and your assumed Gaussian to be minimized. So it's a loss function. So you want to minimize this. So minimizing this means maximizing your log probability and minimizing your KL divergence. Right. Yeah. As I said, in autoencoders, negative log likelihood is your reconstruction loss. Now another question. So KL, QZ, X, PZ에서 PZ가 가우시안을 가정했으니 인코더가 PZ를 따르도록 학습하는 것이 이해하면 되는. 그럼 딱딱 그렇게 이해하시면 됩니다. 네, 요거는 우리의 posterior distribution이 가우시안하고 최대한 비슷하도록 강요해주는 텀이라고 보면 됩니다. 네, 그렇게 해야지 이 posterior가 최대한 가우시안이 되고, 그래야지 이제 x들이 다 이렇게 어떤 가우시안 안에 이렇게 x들이 이렇게 다 포함이 돼가지고 z들이 포함이 되고, 그렇게 해가지고 이제 이 Z 딱 뽑으면 이제 그게 의미가 있는 X가 될 확률이 높아지겠죠. 그래서 그렇게 보시면, so yeah, as 박영서 commented, what this term means is that you want your posterior distribution to be as similar as possible to a Gaussian distribution. So that's what the regularization terms comes for. And in this case, it's a very simple. I mean, the loss function is really simple. The reconstruction term is the same reconstruction term from before. It's just you added one more term, which is KL divergence, and that's it. So it seems really simple, but there's like a lot of insight or intuition behind it. Since you've learned variational inference, we can try to go a bit in depth to learn the intuition behind this derivation. So this was kind of like a neural network point of view. You just set the loss to a certain term, and then you just do gradient descent without knowing the details. It's a neural network perspective, and you can think about it in a probability point of view as well. So probability perspective. So we want to infer PZ given X, and the posterior, so which is a posterior distribution given data X. So this was your decoder this was your encoder in the previous slide, but now it's just some posterior distribution, right? And this is your posterior distribution. So the true posterior distribution is intractable. So you want to have a Q function, which is approximate posterior distribution, QZ given X, and there's it's slightly different from what we've seen in the previous slide, which is the original variational inference. In the original variation inference, it was QZ and PZ given X, but now we have QZ given X. It's not QZ, right? That's because we assume that there's a posterior distribution for each X. There's no global posterior distribution. There's a local posterior distribution for each X. So that's why we have a QZ given X. That's the only difference. So you can see that there's a slightly different term, like here and here. It's slightly different, but the rest is the same. Like this term and this term same. They're still the same thing. Right, and so using QZ given X instead of QZ, because Z is determined by X in our case, because Z is determined by an encoder in variational autoencoder, right? So you derive Z, and then you derive Z. You derive Z first, and then you derive X from Z, which is kind of like cyclic. QZ given X will be our encoder, and in this case, lambda. So lambda is the mu and sigma for Gaussian Q. So we assume that Q is usually Gaussian distribution. So of course, then the parameter of Q would be the mean and the standard deviation. So, and what I'm saying, what this term says is there's a mu and sigma for each X. You derive different Gaussian distribution Q for each X. So like Xi, if Xi goes through Q, then you have mu I and the sigma I. So your encoder will generate unique mu and sigma pair for each X given to the encoder. Right. Then once you have that, you can sample Zi from this distribution, and then sample Zi. You can put it through a decoder, and reconstruct an Xi, which is of course X prime I, and then you want Xi and X prime I to be the same thing. All right. So we want to learn an encoder, which is a posterior distribution, true like optimal posterior distribution, Q star Z given X, which minimizes KL divergence between the approximate and the true posterior distribution. So you just expand that again. So you expand that like this. This comes from the previous slide. Like here, it's the same thing. You expand that, and there's a comparison between the original VI and the VAE's VI, and our new elbow term. So new elbow term becomes this. So as I said, like in the previous VI, I said that this is fixed. In the same manner, this is fixed, right? So you can put this term to here, and then you have the DKL minus this term, which is, and you can, oh, yeah, actually, let me rewrite that. So your log PX is DKL between Q Z given X. I'm sorry. Use Q Z P Z given X and minus EQ log Q Z given X plus log PX X comma Z. Right. So right. Yeah. What I just did, I just moved the term to the left hand side, and then log PX is fixed again, so this becomes your elbow. So this entire thing becomes your new elbow for your variational autoencoder. So previously the previous elbow was this basically. This was your elbow, and now I'm sorry. I got sorry about that. I'm sorry. Not this entire thing this is not your elbow. This is your elbow. This here is your elbow. I'm sorry about that. So log PX is fixed, so you want to maximize your elbow, which leads to minimizing your DKL. And previously in original VI, this was your elbow, but now this is your elbow. And they look a bit different. That's because you're using QZ given X instead of QZ. So that's the only difference between the two. Right? So your elbow is, yeah, compared to this looks slightly different. This term is this term, and this term is this term. That's the only difference, right? And you can actually rearrange it again. So I'm just copying this term to here, right? It's the same term, and then you rearrange some stuff, and then you can derive this term here. So what I did is PX comma Z is PX given Z PZ, right? And then you can separate this term, these two, because there's a log term here. So you can separate the term, and then the first term here becomes this here, and the second term EQ log PZ is combined with this term. So that is combined with this term to derive your new KL divergence between QZ given X and PZ. I hope we have enough time. It's already 48. Yeah, I mean, okay. Let me just quickly go through it to actually explicitly show how we arrive here. I hope that at least this part is clear, because I mean, this is a one-to-one comparison. We had the original elbow. The only difference between the original elbow and this new one is that the Q is now QZ given X instead of QZ. That's it, right? So here is, so far this one is pretty clear. I hope this is pretty clear to everybody. And then you rewrite this to as EQ log P X given Z, and then plus EQ log PZ minus EQ log Q Z given X, right? Like this. And then if you merge this term and this term together, what you get is minus EQ log Q Z given X over PZ, right? Because log PZ, there's like a log term here, and then if you put this together, it'll be minus log PZ inside here, and then it'll be log QZ given X minus log PZ, which is like this, which becomes like this. And now that according to the definition of KL divergence, the DKL between X and Y was sigma X log sigma X log X divided by Y. So this is exactly like this. This is your sigma X is your expectation. So we have expectation of Q and log Q over P. So this is a KL divergence between Q and P, right? So it's, I mean, there's still minus term here, so there's minus term here, and this is exactly a KL term. And now you have this final term here, final elbow. It's a bit like a new elbow. I mean, I rearrange the terms of this, so it becomes this. There's a question in your written equation in elbow phrase plus should be minus. I guess you're talking about this term or some other term. 네, 그렇죠. 이거까지 합쳐서 엘보죠. 네. 아닌가? 이 안에 거 말씀하시는 건가요? 그렇네. 여기 안에가 마이너스여야 된다. 네네네. 네, 맞습니다. 네. 네, 감사합니다. 네. Okay, this should be a minus. I'm sorry about that. All right, so the reason that we rearrange the terms of elbow to this weird looking thing is because one more thing we need to do. So we have the likelihood function here, and we have the posterior function here, right? And you parameterize these functions so that P is parameterized by phi and your posterior is parameterized by theta, because what we're doing is basically we're learning a neural network, right? So this needs to be some neural network. This needs to be a some neural network. This needs to be a some neural network. So we parameterize these two P and Q with like phi and theta, and that's it. So I mean, but the reason that you rearrange this elbow to this term is because it is exactly a minus loss function. So your loss function, which we derive from like here, this was your loss function. When you're thinking about your VA in a neural network perspective, this was your loss function. It was so negative log likelihood plus the KL divergence regularization, right? But now we've gone through all the steps of variational inference and minimizing the DKL, maximizing elbow term and all that. So the elbow term for your VAE is exactly a minus loss. There's a negative log there. I mean, this is log likelihood. There's a minus sign here, so it's log likelihood minus KL divergence, which is the minus of negative log likelihood plus KL, right? So what we've derived here, what we arrived in as a conclusion is that maximizing the elbow is equivalent to minimizing the loss. So which is like really an elegant solution. So just because, in neural network perspective, we just simply added the KL term to force the latent space to follow a Gaussian distribution. And that was your neural network perspective. But that was what that led to us. What led to is that the same thing, you could arrive at the same conclusion with the with variational inference principle. You derive variation inference for your VAE, and then you derive the elbow term, and then it turns out that your elbow term is the same thing as your loss function. I mean, negative loss function. So that's why everything like comes together. So it's a very elegant solution. So yeah, maximizing your elbow is minimizing the loss. So simply adding your regularization term, the KL divergence, is not an arbitrary thing. It's a principled approach. Adding a KL divergence is the same thing as maximizing, like deriving your elbow term. Hope that's clear. Yeah, so your elbow can be maximized by both updating the encoder network and updating the neural decoder network, because now there are two parameters. There's a learnable function here in Q, and there's a learnable function here in P, which is a encoder and decoder. Both are parameterized by theta and phi. So you need to, your elbow term can be maximized by updating or manipulating your encoder and decoder at the same time. So yeah, so you do a gradient descent on both encoder and decoder to maximize your elbow. Yeah. In practice, you update both params together. All right, we only have 5 minutes left. Yeah, I still need to go through the reparametrization trick. Hopefully hopefully this is like all clear. I spent some time deriving all the variational inference to the elbow term, because that is like the essence of VAE actually. Actually, training this is not that difficult. All right, I'm gonna move on then. So how do you train your network? This is the entire step. I mean, yeah, I hope you can remember this. I mean, yeah, I'm gonna go through one step at a time. So you push your X, you sample your X, right? You have a random sample Xi. I'm gonna assume that this is like a sample by sample. Instead of mini batch, I'm gonna assume that you just draw a random sample from your data set. And so your Xi could be like an MNIST image. So you draw a random image and then you push that into your encoder function, encoder neural networks, and then you can obtain your mu I and sigma I. So your neural network look like this. So this is your neural network Q, and then you put X into it, and then it derives a mu, and so this is Xi, your mu I and sigma I. So it's a two-headed function. It's a two-headed neural network. Instead of like generating or deriving the latent Z directly from Q, what you're doing is you're assuming that the posterior distribution is like a Gaussian distribution, right? So what you need to derive is instead a parameter or set of parameters for your Gaussian distribution, which is mu and sigma. So your Q is a two-headed neural network where one head outputs mu and another head outputs sigma. So you obtain mu I and sigma I, and then you can sample possibly many Z's from your Gaussian distribution, which is parameterized by your mu I and sigma I. And that is basically your Monte Carlo you're doing Monte Carlo estimation of your expectation over FZ or your posterior distribution, basically. So you sample, maybe if you don't want to spend too much time, doing Monte Carlo sampling, you can just sample one Z from your Gaussian distribution, posterior Gaussian distribution, actually. Or you can sample like 100 or maybe like 1,000 Z's from your posterior Gaussian distribution. And then once you sampled it, you push that Zi into the decoder, which is another neural network. So this, and then that decoder will give you a reconstructed Xi prime. So you sample from Z here, and then that is pushed through your P, and then you get Xi prime, right? So this is your reconstruction. Then you calculate the squared error loss, mean squared error. So you calculate error loss between this one and this one. There's a MSE loss here. And then you also need to add a regularization term, which is the KL divergence between your posterior distribution, posterior Gaussian distribution, which is this, and your prior distribution, which is a unique Gaussian distribution. And this can be analytically defined because they're both Gaussian. So once you have this, once you calculate this, then you have certain value, which is your loss, and then you can call the backward on your loss if you're doing PyTorch. So you do a back propagate, and then you update theta and phi, which is the parameters for your decoder and your encoder. That's it. That's your training step for a single sample. That's your training step. And I hope that you can imagine how you would write codes in PyTorch to do this. I mean, I hope that you're already like really familiar, not really, but familiar enough with PyTorch that you can imagine how you would go about implementing VAE given this training step. Yeah, there's only one thing. The one thing is that, I mean, this term, you have two terms. You have the MSE term and you have the KL divergence term. And this term can be analytically expressed because this is a Gaussian distribution. This is Gaussian distribution, and the Gaussian distribution here is described by mu I and sigma I. This Gaussian distribution is described by 0 and 1, right? So you can simply calculate the KL divergence between the two Gaussian distribution, which boils down to this term. I mean, you can look it up on the internet to see the general form of a KL divergence between two Gaussian distribution, like DKL of n mu 1 sigma 1 and another Gaussian mu 2 sigma 2. Like then there's like general solution, and if you just plug in 0 and 1 here, then you would arrive here, which is it's a pretty simple format, right? And the mu and sigma is coming from here, the encoder, right? So you you can calculate some value here, some value here, some value here, and then this becomes some scalar value, and then you can plug that into your loss. I mean, this, like, your loss will be like, your loss is like MSE plus DKL. So that is your scalar value in your loss function. What you need to do is you need to calculate this now. I mean, DKL can be used, and then you can update theta, which is your encoder, right? Because mu and sigma was derived, mu and sigma were derived from your encoder, right? Encoder is coming from your encoder, Q theta. So being able to calculate your DKL leads to being able to update your theta in your encoder. So that this part is okay. Like, this part is no problem here. The problem here is this part. Like, can you calculate this and update? Like, this part involves both theta and phi, because x prime I is coming from your decoder, but your decoder depends on your encoder. So both phi and theta is involved in deriving your x prime I. So when you want to minimize your MSE for this term, you need to manipulate both phi and theta. So how would we go about that, doing that? How would we do that? So how about this? The problem is that it involves a random sample zi, because xi prime was derived from a randomly sampled zi. The xi prime is decoded based on the zi, which was sampled from your posterior Gaussian distribution. And so I'm gonna draw a picture here. So there's xi, and then there's q, and you have the mu I, sigma I, then that you can, like, there's a sample zi, then you put it through p, and that becomes your x prime I, right? So yeah, you can. So given x prime I and xi, you can backpropagate through the decoder. Like, you can go through here, like your MSE loss. Your MSE is xi prime minus xi. So given this, you can start doing backward. You can call the backward from your PyTorch, and then you can calculate all the gradients for your decoder, because you can safely arrive here until here, right? Just, you can simply do, consider zi. You can just simply consider zi as an input to your decoder function, p phi, and then you can obtain gradient of your decoder with respect to the loss function, because you can assume that zi is fixed as far as decoder is concerned, right? So you can safely do this, but the problem is, can you backpropagate through the encoder to obtain this term? You can obtain this term, but can you obtain this term? Here the loss being the MSE loss. So can you do that? So that becomes problematic for you. It turns out that it is hard to, or I guess not, I won't say it's impossible, but really tricky to get past the randomly sampled zi. Like, how can you backpropagate through a zi, which is a randomly sampled instance from a Gaussian distribution? Can you do that? Because in all our previous examples, backpropagation was done through a deterministic process. You have an encoder, you have a logistic regression, you have an MLP, or you either have an autoencoder, which are all deterministic. There's no sampling process sampling in the process of from giving the input and then deriving the output. In the input, from the process of deriving, going from the input to the output, there was no stochastic or random element into it. But here in the VAE, there is a random process here. You sample your z from your Gaussian distribution, and that becomes problematic because now it's hard to backpropagate through this operation. So that's where we need to use some trick called reparametrization trick. I hope this is clear. Like, the fact that you can't backpropagate through a random variable, I hope this is is reasonable for everybody. I mean, you can just imagine how you would do about that. Like, I mean, like, how would you, given z, how would you backpropagate through z to arrive at the encoder and try to tune the parameters of the encoder? Doesn't really click in your mind. So yep, so there's something called reparametrization trick, and before we get to that, so we need to talk about the stochasticity in the network. So all the squares or all the diamonds are deterministic node, and the circle node is a random node. So as I said, there's a Q network, there's an encoder network which gives you the mu and the sigma. So until here it's all deterministic. You just put your xi into the Q, and then you derive your mu I and sigma I. So that part is all fixed. That part is deterministic. But then your z is derived from a sample. Your z is sampled from a Gaussian distribution of mu I and sigma I, right? So that's where the randomness comes in. So this z is a random node, and that's why you can't really backpropagate to all the way down to the Q. So instead, what we do is you assume that, well, not assume, you just rearrange, you view z in a different light. So z was a sample from a Gaussian distribution, but now z is a something called mu plus sigma times some epsilon, and that epsilon being a oh, I don't have that, I'm sorry. So your epsilon follows a unique Gaussian distribution. So it's a noise. So there's a separate epsilon node which follows a unique Gaussian distribution, and then you sample a certain epsilon from the Gaussian distribution, and this mu and sigma is still coming from the Q, which receives x. And then you derive z by simply multiplying your sigma to your noise epsilon, and then adding the mu, which is exactly the same as this. Actually, it's your sample from your Gaussian distribution with a certain like mu and sigma it's the same thing. They're the same thing. It's the same as simply adding that mean and multiplying that sigma to a noise sample from a unique Gaussian distribution. It's the same thing. So it's a reparametrization trick. You just view z in a different light, and now your randomness is now outside your entire backpropagation chain, because your backpropagation chain is like here, and which involves the Q function, the encoder function. Epsilon is completely living outside the backpropagation chain, because it doesn't involve any learnable parameter. Learnable parameter is here as a form of theta. So you don't need any backpropagation to this side. So you only need to go here, and everything is now deterministic. Now you can happily just do backpropagation. All thanks to pushing the randomness outside the backpropagation chain. Yeah, so this is called reparametrization trick. So randomness is removed from the backprop path. Yeah. Yeah, so the entire big picture looks like this. So this is we're almost there. So you have an X, which could be like MNIST image, and then you have the encoder, which is parametered by theta, and there's a epsilon, which follows a unique Gaussian distribution. And then given X, your Q generates a mu and a sigma, which is the parameter for your Gaussian distribution. And then you do, using the reparametrization trick, you derive the Z, and then you put that to your decoder, you get the reconstructed X, and then given the reconstructed X and the original X, you get the MSE loss. And of course, you still need the KL divergence term. So that term requires the derived mu and sigma. So they go through the KL divergence, and then, as I said, this is computed analytically. And then you get the final L, and then you can do backprop, and everything is fine, because your backprop path is going through here and going through here. So this and this is all updated. All right. So hope the big picture is clear. Unfortunately, yeah, this should be a GIF, but I guess we can open the link instead. Right. Yep. So this depicts the learning process of your latent space Z. So this is MNIST. You're training an VAE on MNIST images, and these bunch of like pink things are like, oh, sorry. Oh, yeah, I'm sorry. Oops, what's happening here? Okay. Yeah, this bunch of pink things are all zeros, and the blue things are all like 7 and all that. So it is learning, the latent space is like shaping, trying to follow obviously Gaussian distribution. So before, everything was like intertwined, everything was like living inside a single cluster, like 0, 1, 2, 3, all the digits were like all there in the like a sphere. But now, since you're learning the reconstruction loss and the KL divergence term, now your digits are like scattered around in a reasonable manner, and the lower dimensional, your 2-dimensional Z space is trying to look like a Gaussian distribution, and you can sample from your Z space. So, like, your Z in the initial training phase, it won't be anything like really meaningful. Like this is a bunch of noise. So as you can see from the caption here, what you're doing is you're sampling from your Z space, and it's a 2-dimensional Z space, and the first coordinate and the second coordinate, you're just sweeping through -3 and +3. So yeah, your Z is like -3 to -3, -3 to -3 to 3, 3 to 3. Like, it's basically you're sweeping through a grid, starting from -3, 3 to a +3, 3, and you can see that it is learning to generate sensible images from a Z space, and they are, they look pretty nice. Like it's like interpolated examples from, like, a line between -3 and +3. And interestingly, like, the digit 1 is becoming like skewed, and then now it's like, in the right angle, and then now that's becoming more like 9 and 9 as you go rightward, and in the top, the zeros become more like 9s as you go from like left to right. And then, like, if you look at the top right corner, that's like a proper 9, but if you go down and down, that becomes more like a bit similar to 1. So you can sample like novel examples from here, like a distribution of 9s and 1s and 0s. You can sample any Z in this latent space, and then that'll look like a proper number, proper digit. All right, I hope that the visualization was enlightening. Okay, so yeah, this is the end of today's lecture. Yeah, we're like 15 minutes over. Sorry about that. So the conclusion is that VA is an elegant solution for approximating the posterior distribution of P Z given X, and still, it's still an approximation. It's not a true posterior, as I said. You're learning the Q function, not the P function. And the two mapping functions are disconnected, so there's a caveat. So your encoder and decoder they use separate parameters. So the one that maps the X to the latent space, and the one that converts the Z to the actual X, they're separate functions. So there's still a limitation to what it learns. Like, it's not a real transformation from X to Z space. It's just two separated maps between X and Z. And in order to tackle that problem, there's something called normalizing flow, which uses a bunch of invertible functions to map between Px and Pz. So it's no longer an approximate solution. This is an exact solution. You use a set of invertible functions to switch, like, map X and Z from X space to Z space, which is an interesting concept, normalizing flow. There's like different variations of VAs, which like beta VAs and TC VAs, that tries to disentangle the latent space. So we want each Z dimension to have an interpretable role, not just some random number like in PCA. We want the Z space to have certain meanings for each dimension. For example, like Z1 would be like rotation of the image, and Z2 would be like skewedness of the image, and Z3 would be like color of the image. Like, if you manipulate Z1, then only the angle of your image would change. If you manipulate Z3, then only the color of your image would change, something like that. Yeah, and you can even use ZAE to generate sequences or graphs. It's not just for like image generating images or something. You can generate even tabular data or sequences like sentences, or you can even generate like chemical chemical like structures, like graphs. So it's a very versatile framework. Yep. Okay. So that's the end of today's lecture. I hope that yeah, the only thing that the one thing that you really need to remember is this process here. Yeah, this process. In order to implement VAE, you need to follow this exact format, exact steps. I hope that this kind of like these words can translate in your mind into PyTorch code. All right. Okay. Thanks for listening. If there's any question, I can answer them. Other than that, you can. Yeah. Sorry for taking a bit more time than usual. So yeah. If you have any schedule, you can all leave. If you have any question, you can stick around. I'll try to answer any question. Other than
교수님,
that, thank you very much. 네, 예. 안녕하세요.
저희가 이제 이번 주에 추석이 있잖아요.
네네.
그래서 목요일 날 이거를 지금 콜앱을 강의를 못 하잖아요.
네.
그러면은 저희 프로젝트 1 인풋에 대한 정의는 다 다음 주쯤에 이제 나오는 건가요?
예. 제가 추석 끝나고 그 다음 주 화요일쯤에 한번 그 공지를 드리겠습니다.
그럼, 네.
네네. 근데
그,
그 인풋하고 아웃풋은 사실 겐까지 배우고 나서 그 얘기를 드리려고 했던 게 이제 겐을 이용하든가 BA를 이용하든가 뭘 하든가 어쨌든 이미지를 제너레이션만 하면 되는 거거든요. 근데 이제
아,
네 그거를 뭐 그다음 스코어는 우리가 이제 저희가 또 뭐 어떤 그걸 드릴 스코어 매저를 드릴 건데 이제 뭐 라이클리우드를 쓰든 뭐 FID를 쓰든 뭐 심 스코어를 쓰든 그래서 그 얘기를 겐 하고 나서 바로 드리는 게 좋을 것 같아요. 그래서 그거는 다음 주 화요일에 한번 공지를 하겠습니다.
네.
네네. 이거
알겠습니다.
이미 겐하고 VA를 짜셨으면은 프로젝트는 전혀 어렵지 않을 거라서 그건 뭐 너무 걱정하지 않으셔도 돼요. 그냥 이미
네.
짜놓으신 코드, 네. 이미 짜놓으신 코드를 그냥 튜닝하는 정도로만 끝낼 생각입니다.
그 VA 관련된 코드는 그러면은 다음 주에 얻을 수 있는 건가요?
아니요. 이번 주 목요일에 올라갑니다. 그러니까 이제
영상은,
그 영상도 같이 올라와요. 그러니까 이제
아,
그 수업 날 당일에 수업은 안 하지만 유튜브에 영상도 올라오고 클래스홈에 코드도 올라올 거예요.
알겠습니다. 감사합니다.
네. Yeah, just an announcement that even though there's no class this Thursday because of Chuseok, we're still gonna upload the video on YouTube on Thursday and also upload the collab codes on Classroom as well. So yeah, don't worry about that. 서로 다른 디스트리뷰션 K 레벨스 말고 다른 대비를 사용하는 경우가 있나요? 마지막에 넣은 포인트. 베타 VA나 TCVA도 제가 알기로는 베타 VA는 제가 알기로 확실히 KL 다이버전스 쓰고요. TCVA도 아마 KL 다이버전스를 쓰는 걸로 알고 있습니다. 근데 그거 말고 또 이제 뭘 쓸 수 있냐면은 이제 그 KL 다이버전스가 포워드게 맞는지 모르겠죠. 하여튼 리버스 KL이랑 그냥 KL이 있었잖아요. 그거 두 개를 반반씩 더하는 KL이 있거든요. 그게 젠센 샤논 다이버전스라고 JS 다이버전스라고 그러는데 그건 이제 시메트릭하죠. 그건 이제 포워드 KL을 2분의 1, 백워드 KL을 2분의 1씩 더한 게 그 JS 다이버전스가 되니까 뭐 그런 걸 쓰는 경우도 있습니다. 그런 걸 쓰는 VA를 본 적은 없는데 근데 그런 걸 쓰는 뭐 머신러닝 모델을 간혹 본 적은 있습니다. 네. 혹시 뭐 또 다른 질문? Any other questions? 제 생각에는 그 애초에 이름이 VA인 이유가 Variational Inference를 써서 VA인데 Variational Inference는 리버스 K를 쓴다고 그랬잖아요. 그러니까 뭐 거의 항상 VA는 다 리버스 K를 쓰지 않을까 생각합니다. Epsilon, how is epsilon realized during coding? So you just simply sample from a normal unit Gaussian distribution. Just yeah, as I said, like this. In PyTorch, there's a normal distribution function you can sample from. You did that in the previous denoising autoencoders practice. You can use the same thing. You can just sample from a unique Gaussian distribution, epsilon, and then just multiply the sigma to it, and then add the mu to it, and then that becomes your z. Yep. 네. 네, 뭐 질문 없으시면은 오늘은 이 정도로 마치겠습니다. If there are no more questions, I will see you guys next Tuesday. So happy 추석, happy vacation holidays. Hope you guys stay safe, and I'll see you guys next week. Bye bye.